In this video I'm going to introduce the Beaglebone. You may have heard of the Beagleboard or the Beagleboard XM, but this is a lower cost alternative that retains many of the great features. The Beaglebone is a high performance 720 MHz ARM A8 device with 256 MB of DDR2 memory. It has full support for 10100 Ethernet, USB client, JTAG debug via USB. It has 64 GPIOs and 7 12-bit ATDs, and it has support for CAN bus and even for displays through external peripherals. The pin layout is like the Arduino, where you can place shields on the board, and in this case they're called capes because of their shape. It's a fairly low cost device. I think I bought mine for about €80. The Beaglebone boots using the microSD card into embedded Linux. In this case I'm using the supplied Angstrom distribution. In this video I will demonstrate the first steps with the board, and I'll discuss how you can use embedded Linux to send or receive values to the input-output pins and the 4 onboard LEDs. Here's the Beaglebone. It comes packaged like this. Open it up. We have the Beaglebone. It comes with an SD adapter, an SD card adapter to standard SD size, and it comes with a USB cable to allow us to power it over USB. So the Beaglebone itself, it's a fairly neat device. You can see it's a fairly small form factor. If we compare it to the Beagleboard XM, you can see that's the Beagleboard XM. So you can see it's around half the size, just slightly over half the size of the Beagleboard XM. So it's a neat board. You can see here we have the Ethernet connection, we have the 5 volts power supply, we have the USB in, we have the USB out that can be connected to USB hub, and we have the SD card. So it comes with a 4 GB SD card as well. So here is the top of the Beaglebone. Here we can see we've got our main processor, which is the AM3359 in this case. In later revisions it's going to be replaced by the AM3358, and as a result certain features won't be available on this version. Here we can see we've got our USB hub. Over here we've got our FDTI. This is our USB to serial converter. It also provides support for JTAG. And finally over here we've got our memory. This is a 256 megabytes of DDR2 memory. We have the expansion headers. This is expansion header A, this is expansion header B. Over here we have some user LEDs that we can control directly from within our programs, and this tiny little reset switch here up at this point allows us to reset the board. There are two ways to power this board. We can either power it using the 5 volt jack, center male jack, or we can also power it via the USB, via the mini USB adapter. So in this case we're going to use the mini USB and plug it in, and that will now allow us to mount. You can hear the beep in the back. That mounts this device. You can see the user LEDs flashing, and it allows us to mount it as a storage device under our Windows machine, for example. One problem with this is that we are limited though. This board is limited to 500 MHz when it's USB powered. If you power it through the jack, you're able to run this board at 720 MHz. Finally, I'm going to connect this to my network using a standard Ethernet patch cable. Plug the cable in here. It's a 10100 Ethernet adapter, and I'm just going to reset my board to put it on the network using DHCP to organize its IP address. The first thing you need to do when you get your Beaglebone is to download the latest distribution. You do this at beagleboard.org/bone, and down at the end of the page you'll see there's a link here to download your Angstrom distributions. So here's the directory for the distributions, and I'm going to install Angstrom Cloud IDE, and I'm going to install the version from the 11th of the 1st 2012. So you download that. It's a GZ file, gzip file, and you decompress that to a directory so that you have an image file in that directory. Okay, so we're going to write the new image to the Beaglebone. First thing we do is power down the device. So in this case I'm using USB for power. So we power down the device. I'm going to take the SD card out of my Beaglebone, and use the adapter, the micro SD adapter. I'm going to use that then to and plug this directly into my computer. Okay, I've plugged the SD card into my computer and it appears as on the K drive, Beaglebone getting started, so I know I can use that from my card reader. And as recommended on the website, I'm going to use the Win32 disk imager. This is because I'm using a Windows machine, which means that I'll have to image this Linux, format this drive in a Linux format. So I choose my SD image, and then I choose my device, which is K. And that means now that I'm able to write this SD image directly to the SD card. So we continue. And it takes a little bit of time. It's transferring there, so it'll take a bit of time. Okay, so it's almost finished. It's finished right into the SD card. So the next thing now to do is to place the SD card back into the Beaglebone. Once we plug the USB cable back into the Beaglebone, up pops an autoplay window in Windows, and we can open the folder to view the files. And in here you'll find documents, and you'll also find drivers. Now you don't need to install the drivers yet. You'll install them later on if you're using Code Studio, or if you're using if you want to debug the applications in more depth, but you don't need to do that for the moment. The next thing we have to do is find our Beaglebone on the network. Once you've plugged it into your router, you need to actually determine what its IP address is so that you can connect to it. To do this, I'm going to use a port scanner. This advanced port scanner can be downloaded freely, and we can scan in the IP address. My DHCP allocation is above 100, so we can scan all of the devices on our network, and we can find the different devices, and up pops, let me see if they got names. Got different devices, so hopefully we find the, okay, I think this is the one. If we open it up, we can see that, yeah, open ports 1. You can see that the only open port on this device, which is the Beaglebone, it's decided it's 192.168.1.112. You can see port 22 is SSH, secure shell, so it means that that's the port that we want to connect to on that device. So I'm going to use PuTTY to set up and connect to my Beaglebone on the network. So to do this, we need to enter in the IP address, which is 192.168.1.12. And we're going to connect to port 22 through SSH. And I'm going to save this as Beaglebone. Okay, so save this. The other thing that we might want to do is we might want to allow X11 tunneling, so we can enable X11 forwarding through our port. I'm just going to use colon 0.0. Okay, so go back to my session again and save that again. Save. Okay, so we'll open up that connection, double click, and it pops up potential security breach. So we'll accept this. It's a new fingerprint. We go yes, and this will give us our terminal shell to this port. And initially, when we connect to this device, we log in as root, and the password is root. Okay, so straight away we can cd slash ls-al. We can see that we're onto our Beaglebone, and we can see that we've our Linux. It looks like any normal Linux device. Probably the first thing we want to do is change the password. Change the password from root. So we have a new password for this device. The next thing that I'm going to do is I'm going to start the Cloud9 Integrate development environment, the server for that. So if we started, we can just type Cloud9 ampersand just to run as a background process. I'll just give it a second, see what messages we get back. Okay, so it started correctly, and it's told me that it's running on port 3000 on my Beaglebone. Just check, yeah, that's returned correctly. So we can open up our web browser and open up this port directly. So 192.168.112:3000. So it's connecting to our Beaglebone. It's loading the Integrate Development Environment interface. And here you can see it looks exactly like any software development environment. We're able to connect to it directly. So here we can see We've our Cloud9 project. There's a good guide there. There's good information on how to develop using this framework. And you can see we've simple examples like this one here. So if we go, for example, to Blink LED, we can see that this little piece of JavaScript code allows us to set up our user output pin, or one of our Bone LED output pins. We have our setup function, which sets up our 2 LED pins as output pins, and then we can write a high and a low to these pins, delayed by 1000 milliseconds each. So we can execute this directly by pressing the run button, and this is quite interesting what happens. Well, when I press this, we can see that on our Beaglebone, we can see we now have LED 3 is flashing at 1 second intervals. So that worked perfectly. What's interesting is that if we actually look at what's going on, if we go back to our shell, we can actually see we can actually see that there's our Blink LED running. So it's running as node/var lib cloud9 blinkled.js. So when we press play in the development environment through the web interface, we're actually executing a process on the Beaglebone directly, which is quite a nice feature. We can kill this directly here. We can press the stop button. It's probably a little bit cleaner. We can press stop, and that stops our application from executing. So if we go back to our shell again and do the exact same thing, we can see now that blinkled.js is no longer running on the machine. So that's the way that this environment integrates with the Beaglebone and with the Linux operating system underlying it. The server is executing processes on the local machine, and it's quite a neat way to program. There are some more complex examples here. There's an example of running a server, and this allows us to mount a web server on port 80 of the board. Instead, I'm going to look at how we can interface the Beaglebone to external circuits. And to do this, I've built a very simple light sensing circuit that uses a LDR, or light dependent resistor, along with a 10k resistor in a voltage divider configuration. I'm using one of the analog to digital converters that's present on the Beaglebone. These are 12-bit analog digital converters, and I'm using 3 of the lines on the Beaglebone. The first line is the red line, which runs to the input side of the LDR. It's coming from pin 32 on the P9 header of the Beaglebone, and it's labeled VDD ADC. This is the voltage supply for the analog digital converter, and this is very handy because it's a 1.8 volt supply, and we have to be very careful that the analog to digital input pins only allow up to 1.8 volts. That's different than the 3.3 volts on the other pins. So that's connected to the LDR, and on the outside of the LDR, even though it doesn't matter which order they're in, we have connected to the 10k resistor, which runs back to the analog to digital conversion ground ADC, which is pin 34 on the P9 header. And finally, in between, we connect the pin that we want to measure, which is our this is indicative of the light level in the room, and we're using this as AIN 0, which is pin 39 on the P9 header. So this will give a voltage value less than 1.8 volts, depending on the light level in the room. So here I am in my shell, and the first thing I want to do is I want to go to the device itself. So the pin AIN 0 is the pin that we've connected to, which again is pin 39 on the P9 header. And to do this, we're going to go into /cd/sys/devices. And here we can see a list of all our devices. Well, if we go to platform, ls, so we can see all of our devices, and we can read values in from these pins. The particular section that we need, TSC, and we're going to read in from these pins. Now, I'm not sure of the naming convention here, but AIN 0 on the Beaglebone, the analog input 0, is actually AIN 1 when it's mounted as a device, which is a little bit confusing. So AIN 1 is the value that I want to read. So I can do this by typing cat AIN 1. And you can see here it's 3879 is the value that we read in. So based on the normal light level, we've got a value of 3879. We can read it, we can try it a few times. You'll see it moves around a bit from 3879 to 3830, 3870, 3880. It'll move around a little bit depending on the light levels. If I cover it with my finger, so I'm going to cover the LDR with my finger, and I read in the value again, you can see it's after dropping significantly down to 2946. So I'll read it in a few times. My finger's still over the LDR, so you can see that I'm blocking the light level, so you can see it's dropped off very, very much. The other thing I can do too is, well, let's just check. I take my finger away from covering it, and you can see it goes back up to where it was, 38749. And if I bring the torch right down on top of the LDR, so I've brought my light right down on top of the LDR, we can read it in, and we can see we're getting 4082. Try again, 4082. It's quite consistent, which is interesting because the upper bound on this is 4096, will be the highest value we would read in if we're reading in from this port. And this is because we're using 12-bit analog to digital converters. 2 to the power of 12 is 4096. So therefore we get a value between 0 and 4095, which is 4096 individual values. In this case we're using a very tight range. We're not going near the value of 0 at all, and that's because of the way that this voltage divider configuration is set up. If you wanted to use the full range, you could spend time designing an appropriate resistor configuration. One other thing that we might want to do is to interact with the LEDs that are beside the network port on the Beaglebone. To do that, we can go to the devices. We can go to Sys, Devices, and it's in Platform. Just do an LS there. You can see we can go LEDS, GPIO, and we have our LEDs here. And we can here we have our 4 user LEDs. So we'll go to the third one. So we can go to Beaglebone USR3. And we can, oh, I did wrong there. Oh, I forgot to put the 3 in. So we got the third one, and we can see brightness. So it's possible for us to, for example, echo a 1 to brightness, and we can see on our board that this turns on the LED 3. We can do we could echo 0 to turn it off. And this turns off the LED on the board. So I hope you found this initial video on the Beaglebone useful. It just showed the initial steps of getting started with the Beaglebone. You could use the later material on embedded Linux calls to write fairly advanced scripts and to send and receive values to the input-output pins. I will follow this video up with a video on writing applications that execute on the Beaglebone. Thank you.